Hi everyone and welcome to the next lecture in machine learning for core engineering disciplines. We have now got into nonlinear dimensionality reduction, which is a type of unsupervised learning. So in the last class we finished the lecture with a discussion of the uniform manifold approximation and projection, which is a very recent nonlinear dimensionality reduction technique only introduced in the year 2018. So we will see how that works. We will continue our discussion from last time. So the topic today is UMAP. And what we are trying to do here is we are trying to reduce the number of dimensions. So it is very difficult to of course represent the number of dimensions here, but one can draw something like this, right. So here you have, we are working in p dimensional space, right. So you have n points, right, each with p features, and you want to reduce that, right, to a d dimensional space, right, where these are your points and the number of dimensions you are working with is much lower. Okay, so you want the data y, right. So here again you have n points, but you are in a lower d dimensional space. Okay, so that is what is happening here. So how does this work, right. So what we had discussed last time is, to do this we want to preserve global structure as well as local structure. While mapping points from high to low dimensions. Okay. And to start out with, we had found the k nearest neighbors, right. So these were the steps. So we found the k nearest neighbors of each point xi, right, and then we needed a scaling factor, right, for the probability. So that was the distance to the nearest neighbors, which we said was the minimum distance among all the dij's, right, the distance to other points where dij is greater than 0. So we exclude the point itself, and then we had these asymmetric probabilities as exponential of minus dij minus rho I divided by sigma I, where sigma I was obtained by maintaining roughly the number of neighbors to be k by solving this equation. Okay, so that is what was happening. So this is how sigma I is determined, right. So you have to plug in the pij's, they come from the above equation, and thus you get a value for k, and you already know that k is the parameter which is the effective number of neighbors. Okay. And finally the probabilities were symmetrized. So we computed the symmetric probabilities, and they were defined as Pij, capital Pij is small Pij plus Pji minus Pij Pji. Okay, so this is all what we had done in the last class. Now like we said, we have to have a similarity metric in the lower dimensional space. So we then define the similarity in the lower dimensional space. Right, and we had said that this has d dimensions. So that is again something that you have to tell the algorithm, right, just like you would have to tell the TSNE algorithm, you have to tell the UMAP algorithm in how many number of dimensions do you want the new data set in, right, and that will determine the number of variables for the optimization of in TSNE we worked with the KL divergence, the Kullback-Leibler divergence. Here you will see we will work with the cross entropy, and that function would have to be minimized with respect to y1, y2 up to yn, and thus the number of parameters, right, will come into the picture. So how the similarity metric is defined is as follows. It is defined as Qij is 1 divided by 1 plus a yi minus yj norm squared to the power b. Okay. So here xi, as you remember, is mapped to yi, and xi is a vector of size p, whereas yi is a vector of size d, and obviously you want d is typically much lower than p, right. If you want much lower dimensional space, that can be done, or at least it should be lower than p. So what we have done here is essentially we want these, right, constants, these are already specified, and then we are able to map, right, yi's so that the cross entropy between Pij and Qij is minimized, right. So these a and b, these are constants learned to match the structure between the low and high dimensional spaces. So a and b are constants learned to match the structure between the low and high dimensional spaces, and essentially it is learned by mapping, right, this function 1 divided by 1 plus a d square to the power b to basically represent the kernel, right, e to the minus d, right. So this is the type of kernel, right, that was used in the high dimensional space, and this is a much simpler kernel that we are using in the low dimensional space, and a and b are the constants to learn that kind of structure. And finally the last step, right, step C, involves determining yi's by minimizing, like I said, the cross entropy between the distributions p and q. Okay. And in this case, like I mentioned, you do not use the KL divergence, you minimize the cross entropy. So that is sum I less than j, right, because we are dealing with pairs, Pij log of Pij divided by Qij, plus 1 minus Pij log 1 minus Pij divided by 1 minus Qij, right. So, this is a type of cross entropy, and if you minimize this, right, with the yi as the parameters and yi exist in a lower dimensional space, then you have effectively done your dimensionality reduction. Okay. So, this is how basically the UMAP works, and the advantage is that due to the use of the cross entropy, right, this term, you are also looking at the probability of the points not being close, which means the points are far from each other. So, essentially due to the use of this cross entropy, not only do you pull neighbors in the high dimensional space, closer in the low dimensional space, and that happens due to this first term here, right. So, this term has the role that it pulls together, right, points that are closer in the high dimensional space and makes them lie closer closer in the high dimensional space and makes them closer in the low dimensional space. And the second term, right, but also we pull apart far away in the high dimensional space, we pull apart far away points in the high dimensional space from lying too close in the low dimensional space. Okay. And that is essentially the role of this second term here, right. So, you see the kind of subtle differences that is done with the TSNE and with UMAP, and this brings me to the end of the discussion on UMAP. So, this algorithm, right, UMAP, it preserves both local and global structure, right, as opposed to TSNE, which is really better only for the local structure. Alright. So, I hope you understood the differences between these. We will of course try to take up some more practical examples rather than the math in one of the future sessions. And before closing this lecture, I briefly want to discuss the concept of autoencoders, right, which is the fourth type of dimensionality reduction we are discussing. We already discussed PCA, which was linear dimensionality reduction, then TSNE and then UMAP, and the fourth one is autoencoders. So, autoencoders, these are a neural network based solution. These are a neural network based approach to nonlinear dimensionality reduction. Okay, so what happens here is you have data in the high dimensional space, right. So, that is passed through an encoder. So, this is data in high dimensional space, okay, and this construct which is made using a neural network is called an encoder. The encoder brings you to what is called a latent space, okay. So this is the latent space here, which has fewer dimensions, which is essentially data in a lower dimensional space. Right, and how do we know that the latent space is a good representation of the high dimensional space? We need to have a decoder, right, which will tell us, right, whether if we go back from the latent space to the original data space, do we reach the same point, right. So you do need a decoder, right, and hopefully you come back to the data in high dimensional space. So you have to check how well you can reconstruct, right, the high dimensional space from the latent space. And now these two, right, the encoder and the decoder, these are both neural networks, right. So you do have to tune the parameters inside the neural network, and that is an important part of training the neural network. So essentially what is happening here, if you want to write down, so the data points in higher dimension are encoded into a lower dimensional space, and this is through a neural network, and then the decoder verifies, right, you do need to check that the latent space is a good representation. So decoder verifies that the original data set can be approximately reconstructed from the latent space. And for those of you who do not know, the word latent means hidden, right. So it is like a hidden space, right, which you did not know before you had developed the encoder and the decoder. And obviously at this stage we are not in a position to learn about this encoder and the decoder. So the encoder and the decoder, these we can only learn once we know the tools and concepts of neural networks. So this has to be done in a future lecture. So once we have completed the concept of neural networks, we will come back and look at the concept of autoencoders, and there we will discuss what kind of loss function is to be used and how can we ensure that the encoder and the decoder are working properly to give you the autoencoder, right. But I hope that the gist of the method is clear, that you go from the original data, right, which is in a high dimensional space, to a latent space which is a lower dimensional space. Of course you have to develop this encoder and decoder architecture, which is a neural network, but you can see clearly that you can extract out a lower dimensional space here. So this brings me to the end of our discussion on unsupervised learning. We spent quite a bit of time learning about clustering algorithms, right, such as k-means clustering, k-medoids clustering, as well as density based clustering, which is very good where you have noise or outliers, so that you bring points that are in high density regions right, and cluster them together. And then we also looked at dimensionality reduction algorithms, which are very important to demystify what is going on in very high dimensional spaces. So whether you are doing linear dimensionality reduction through PCA, principal component analysis, or you can implement nonlinear dimensionality reduction through the use of techniques like autoencoders as well as UMAP, TSNE, and other algorithms that you may come across. So I hope you learned something new from this lecture. Thank you for joining, and I look forward to seeing you next time.